I am Sunil Deshpande and we are going to discuss motion of a charged particle in a combined electric as well as magnetic field. More emphasis will be on the motion of a charged particle in a magnetic field, but in a couple of problems I have even taken the electric field also. Okay, so what I should make you remember here is, or through my problems which I am going to discuss further, what I have highlighted is, for the charged particle to experience the force due to the electric field, the charged particle could be at rest also, or it can be even moving also. And if it is moving, it does not matter how is it moving, whether it is moving in the direction of the electric field, opposite to the electric field, make some acute angle, obtuse angle. So, irrespective of whether it is moving or not and irrespective of the direction of its velocity, it is going to experience the force due to the electric field. This is what you should remember. So, you cannot escape, you in the sense the charged particle cannot escape experiencing the force due to the electric field. Okay. But when it comes to the question of experiencing the force due to the magnetic field, you should remember that it is given by the formula Q V cross B. So, if there is no velocity, there is no question of any force due to the magnetic field on the charged particle. But when there is velocity and the angle between velocity and magnetic field is either 0 or 180 degree, still there is not going to be any force due to the magnetic field on the charged particle. Fine. Only when the angle is not 0 and 180, charged particle will experience the force, and if it does not have any velocity, no question, right. So, with the different problems that I am going to further take, I have tried to highlight all these issues, and we will see, we will enjoy the problems. So, here is the first problem on motion of a charged particle inside a magnetic field. So, let me tell you that the force is given by the cross product. So, you will have to be very clear about the direction as well as the magnitude of the force experienced by the charged particle while moving in a magnetic field. But let me first tell you that the charged particle would experience the force only when it has got the velocity. This is the first requirement, because in an electric field the charged particle would have experienced the force even when it had no velocity or it was at rest, right. But now in magnetic field it will experience the force only when it has got the velocity. That is the first requirement. And second requirement is the velocity should not be in line with the magnetic field or opposite to the magnetic field, because if the angle between velocity and magnetic field will either become 0 or 180 degree, the force experienced by the charged particle due to the magnetic field would be 0. Of course, all these things are what follow when we write the formula for the force experienced by the charged particle, right. So, we will read the problem first. A positively charged particle moving with a velocity v enters a region with a constant magnetic field B. The magnetic field is constant, but the velocity v is still in the form of a vector, and you have got the liberty to project the charged particle into the magnetic field in whatever direction that you want. Okay, the particle will experience maximum force when the angle between velocity and magnetic field is. Very simple theoretical question. So, anyone who remembers the formula for writing the force experienced would immediately declare the answer. So, let me write that. So, F equals Q V cross B. The force is given by Q V cross B. Therefore, if the, or you can say the magnitude of this cross product will be Q V B sin theta. So, for the force to be maximum, theta should be equal to 90 degree, because sin theta will be 1 and the maximum force will be Q V B, and that is possible when you project the charged particle at right angles to the magnetic field. So, the correct answer here is B. Okay, so here is one more theoretical question, a very simple one. Let us read it first. The frequency of a charged particle moving at right angles to the magnetic field is independent of. Okay, so frequency means, see, he is projecting the charged particle at right angles to the magnetic field. So then it's for sure that the force that the charged particle is going to experience will be maximum, and moreover the trajectory or the path described by the particle will be a perfect circle. So what he means by frequency here is the reciprocal of the time it is going to take to go round once. Fine. So 2 pi r will be the distance which the particle is supposed to cover. Let us see what is the frequency of rotation. Okay, so what is the force? You can write F equal to QV cross B, and because the angle is 90, I can write the force as F equal to QVB, right? And this force itself will provide the necessary centripetal force for the particle to undergo circular motion. Therefore, I can equate this to mv square by r. Fine. Okay, but how did I realize that the force will be centripetal? It is because by the rules of the cross product, this force is going to be always perpendicular to the velocity, and we can call that force which is perpendicular to the velocity as radial or centripetal, and therefore the particle here will describe a circular motion, and I have equated this force to mass into acceleration. M is the mass and v square by r is the centripetal acceleration. So you get r is equal to mv by qb. R is mv by qb. So this is the radius. Now what is the time taken by the particle to go round once? Let us calculate that. So time will be given by distance by speed. Distance is 2 pi r and speed is v. So if you substitute the value of r by v, you get m by qb. So it will be 2 pi m divided by qb, right? R by v is m by qb. So 2 pi m by qb. This is the time that the particle is going to take to go around the circle once. Now if you want to calculate the frequency, it's just the reciprocal of this time. So 1 by time period is nothing but qb by 2 pi m. So qb by 2 pi m. And now you can select the options. Fine. So reciprocal of the time period is frequency, and that is nothing but qb by 2 pi m. Okay. It's independent of the radius. Right. It's independent of the speed, both a and b, and the magnetic field. These are the options. It is independent of the magnetic field is ruled out, because in the expression you are clearly seeing the presence of the magnetic field in the numerator. So now it is independent of radius also, and it is independent of speed also, because there is no expression for speed as well as the radius. So both a and b are correct. So this is the right option. So one more theoretical question regarding the charged particle experiencing a force in the magnetic field. See, a charged particle moving in the positive x direction is subjected to a magnetic field in the negative x direction. As a result, the charge will retard along the x-axis, move along a helical path, remain unaffected, starts moving in a circular path. Okay, so this I think will again remind us about how do you write the force experienced by the charged particle. It is given by F equal to QV cross B. Fine. So that shows that the force is perpendicular to the velocity, and not just that, there will be no force experienced by the charged particle provided velocity and magnetic field are either parallel or anti-parallel. So here the charged particle is moving in the positive x direction and magnetic field is in the negative x direction. So what is the angle between the velocity and the magnetic field? 180 degrees. And while writing F equal to QV cross B, if the angle between V and B is 180, then sine of 180 is going to be 0. So the force experienced by the charged particle will be 0. So no question of retarding, no question of moving along the helical path, no question of moving in a circular path. So the correct option is it remains unaffected. So there is one more simple question here on the motion of the charged particle in a magnetic field. A uniform magnetic field is at right angles to the direction of motion of an electron. See, he has already told you that the field is perpendicular to the direction of motion of the electron. So it is going to experience a maximum force. The radius of the circular path is 2 centimeters. So it will experience a maximum force, that is one thing. And second thing is, the force being perpendicular to the velocity by the rules of the cross product, the particle will start undergoing a circular motion. Fine. So the radius of the circular path is given to be 2 centimeters. Now he is going to double the speed. If the speed is doubled, radius of the path described by the electron is going to become how much? Fine. So that's the question. So if you just recollect the expression for the radius that we had written in the previous problem, that was r equal to mv by qb, you can clearly see that mass is constant, charge on the electron is constant, and even the magnetic field is constant. So your radius is directly proportional to the velocity with which the charged particle is going to be projected at right angles to the magnetic field. So in the question, if he says the speed is going to be doubled, the radius is also going to be doubled. So initially the radius was 2 centimeters and now the radius will become 4 centimeters. The correct answer is A. So here there is one more, but the speciality or the beauty of this particular problem is you will now have a combined electric as well as the magnetic field, and we will have to discuss about the motion of the charged particle in such a combined field. So uniform electric as well as the magnetic fields are present in the same direction. Okay, fortunately both the fields are in the same direction. An electron is projected also in the same direction. But remember, it's an electron, so negatively charged particle. Options are, its velocity will increase in magnitude, its velocity will decrease in magnitude, it will turn to its left, it will turn to its right, and so on and so forth. Now, there is a combined electric and magnetic field, and you have projected the charged particle, whether it's electron or proton, in the direction of the magnetic field itself. So the angle between velocity and magnetic field is 0, and the force experienced by charged particle due to the magnetic field being given by the cross product, sin 0 is 0. Therefore, it will not experience any force due to the magnetic field, right? But for the charged particle to experience the force due to the electric field, it is not important whether the charged particle is at rest or is moving, right? So it will definitely experience the force due to the electric field. But by the definition of the electric field, it is always in the direction in which a positively charged particle would experience the force. But electron, being a negatively charged particle, will experience the force not in the direction of the field but opposite to the field. Therefore, the charged particle is projected in the direction of the electric field, but it will experience a force opposite to the electric field. Therefore, it will keep on retarding. Hence, the correct answer is its velocity will decrease in magnitude, right? And there will be no change in its direction. So no question of changing towards its left or towards its right, because this force which the charged particle will experience due to the electric field will be 180 degree opposite to its velocity. So no direction change, only the magnitude reduces. So second option is perfectly correct. So there is another question here. The work done by a magnetic field on a moving charged particle is. The work done by a magnetic field on a moving charged particle is. See, just now we have been seeing that the force experienced by the charged particle in a magnetic field is always perpendicular to the velocity, F equal to qv cross b. So by the rules of the cross product, the force is always perpendicular to the velocity. So when the force is perpendicular to the velocity, the work done by the force is going to be 0. because displacement is always going to be in the direction of the velocity, force is perpendicular to displacement, angle between force and displacement becomes 90, work done is defined as the dot product of force and displacement, it involves cos theta, and when theta is 90, cos 90 is 0. Therefore, the work done by a magnetic field on a moving charged particle is 0. So, see here, it is irrespective of how you are going to project the charged particle in the magnetic field. That is, whether you project it at right angles to the magnetic field and make the charged particle experience maximum force, or you project the charged particle making some other angle with the magnetic field. Irrespective of this, the force is always going to be perpendicular to the velocity and so displacement, and therefore, the work done is always going to be 0, and the correct answer is this. So, one more theoretical question. Radius of curvature of a charged particle in a uniform magnetic field is directly proportional to. See, in the previous problem we had written the expression for the radius of a charged particle moving in a magnetic field, and that was R is equal to mv by qb. So, this was the expression for the radius of curvature of the path described by a charged particle moving in a magnetic field. Now, if you just remember this, I think you can answer this question. He says it is directly proportional to the momentum, and that is perfectly correct, because you see that momentum in the numerator, mass into velocity. Directly proportional to the intensity of the field is wrong, because it is in the denominator, inversely proportional. Charge on the particle is also in the denominator, so inversely proportional. Energy, there is no energy expression there. So, the correct answer is it is directly proportional to the momentum of the charged particle. So, this is the right option. So, there is one question connected with the work done by the magnetic field force which is acting on the charged particle while it tries to move in that field. So, read the question here. When a charged particle moves in a magnetic field, its kinetic energy always increases, always decreases, remains constant, or may increase or decrease depending upon the direction in which you have projected the charged particle. Fine. So, let us not forget here that the force which the magnetic field will exert on the charged particle is always going to be at right angles to the velocity. So, F dot V is going to be 0. The force is perpendicular to the velocity, so F dot V is going to be 0, and if you know, F dot V is the power. So, power delivered by the magnetic field on the charged particle is going to be 0, and when the power delivered is 0, the work done by the magnetic field is going to be 0. So, change in kinetic energy is going to be 0. Fine. So, because work done by all the forces is equal to change in kinetic energy, the only force which is acting on the charged particle here is the magnetic field force. That being perpendicular to the velocity, power delivered by the magnetic field force is 0. So, when the power delivered is 0, work done is 0, because power is nothing but work done divided by time taken. So, when power is 0, work done is 0, and when work done is 0, change in kinetic energy is 0. Therefore, the answer is it remains constant. Change is 0. So, it remains constant is the answer there. So, this is the right option. So, there is a beam of protons here which is deflected sideways, that has been assured to you. A beam of protons is deflected sideways. Now, this deflection might be caused by, I would want you to stress this word might be. Please remember, might be caused by. First option, magnetic field only. Second, electric field only. Third, either electric field or magnetic field. Both electric and magnetic field. Right? So, see, he says this deflection might be caused by magnetic field only is wrong, as if the electric field cannot deflect our beam of protons, isn't it? Can the beam of protons be deflected by an electric field also? Yes, certainly, because if the electric field is at an angle to the direction in which the beam of protons is travelling, then definitely the beam of protons is going to be deflected sideways. Okay. Second, electric field only, not at all. Magnetic field can also do this job, because had you taken the magnetic field at say some angle with the velocity of the beam of protons, then definitely there would have been a deflection, because QV cross B would have been the force experienced by the protons in the presence of the magnetic field. So, we cannot say magnetic field only, electric field only. Either electric field or magnetic field. It can be caused either by the electric field or by the magnetic field. Of course, I think we would have agreed to this particular option had he not raised one more, both electric and magnetic field. So, this might be caused by both. I think this option seems to be more correct as compared to the third one, C, right. So, the correct answer here is both, because the deflection might be caused by both electric and magnetic field. If he says either electric or magnetic, as if both of them, in the presence of both of them, our beam of protons is not going to be deflected, isn't it? I hope you agree with me that the third option makes you feel that had the two fields been there simultaneously, our beam of protons would not have got deflected sideways. Fine. So, I think we should go with the fourth option. A charged particle is whirled in a horizontal circle on a frictionless table by attaching it to a string fixed at one end. So, the string is fixed at one end, and to the other end of the string there is a small charged particle which has been connected, and it is being whirled in a horizontal circle on a frictionless table. See, here the circular motion being described is on the horizontal table. If the magnetic field is switched on vertically, tension in the string will, right, will it increase, will it decrease, will remain the same, or may increase or decrease. See, he has not told you what charged particle it is. Is it a proton or an electron? Means a positively charged particle or a negatively charged particle, that is one thing. And secondly, he says the magnetic field is switched on only vertically. Whether vertically upwards or vertically downwards is also not known. So, let us imagine one case. If you consider the charged, and moreover one more thing, that charged particle is moving in a circular path in the clockwise direction or anti-clockwise direction is also not known. So, because of these three things, I think we will not be in a position to decide whether the tension will increase or decrease for sure, right. So, the answer is going to be may increase or decrease, but let me explain you. See, this is the horizontal table and this is the charged particle, say positive, and it is moving in the anti-clockwise direction, fine, and you switch on the magnetic field vertically upwards. So, it will experience the force given by the formula QV cross B. So, V is like this, B is vertically upwards, so angle between V and B will be 90. So, QV cross B will be Q, V is on the table, B is upwards, so V cross B will be like this. Cross product is given by our thumb rule, so V cross B will be outwards and perpendicular to velocity. Perpendicular to velocity means always radial, because in a circular path velocity is always tangential. Okay, so the tension in the string is also radial, and this force which our charged particle has started experiencing is also radial, but the tension is directed towards the center and the force is in our case now away from the center. So, how do you write your equation for circular motion? That is F equal to ma, F which is in the direction of acceleration. This is what I have been telling you always. The force in the direction of acceleration should be taken as positive. So, I have taken the tension which is towards the center, right, centripetal acceleration, please remember. So, F towards the center, that is the tension, is taken as positive. So, T minus QVB is equal to mv square by r. So, T will be equal to mv square by r plus QVB. So, this shows that the tension has increased, but this is only when you assumed a positively charged particle going in the anti-clockwise direction with the magnetic field switched on vertically upwards. Fine. So, if you just look at the free body diagram, you will realize that it may increase or decrease, right, because of the ambiguity in the direction in which the particle is describing the circular path, direction of the magnetic field, whether vertically upwards or vertically downwards, and secondly, this charged particle being positive or negative. So, D is the correct answer.